This meeting is being recorded.
Okay. So, all right. So my session is time series modeling, and so see, doing it in Python or R or any other standard software package is just running the software. So I will slightly get into the theory, maybe about an hour or so, and then we will do the Python coding. I mean, Python coding, as far as I understand, can always be learned from, nowadays you have so much of resources on the net. And so you can learn the coding on your own if required. However, the theory might require a little bit of concepts. And so let me then therefore do the theory a little bit. But if you have any questions, do feel free to ask. I'm still, even after 2 years, I'm still very uncomfortable in this online mode. I can't see you. I can't, understand whether you're able to follow what I'm saying and all that. So if you have any doubts, if you are not following anything, please do feel free to stop me at any point of time. Otherwise, I'll just keep talking. All right. So, okay. So we will get, let me first share my screen. Yeah, my screen is visible. One thing that I can do is probably remove my, okay, there are other people. Okay, I'm putting my video off. Okay, there are some people still entering. So just remind me after a couple of minutes to check back. Huh? Okay, so I hope my screen is visible, but if it is not, do feel free to stop me. Okay. So we are looking at time series analysis. Just 1 minute. So we will be looking at time series analysis. So what is a time series? Anybody can tell me what is a time series? Any idea? Have to talk.
So it will be one variable measured over a span of time.
Yeah, fine, great. So can you give me an example of a series that is not a time series and a series that is a time series? Very good answer. Yeah.
So the price of what you call, say, crude oil, right? So over a period of time, that would be time series.
Right.
And thinking about something that is not a time series,
Sorry?
probability, so probability of somebody passing an exam, right? So, say for example, the UPSC exam, the passing rate.
Scores, yes. The scores will not be a time series. It will be a snapshot at one point of time. Yes. So that the scores of any class, the height of some people are taken at one snapshot. Or if you are doing marketing, then it's the brand equity of various products at a snapshot in time will not be a time series, whereas the brand equity of a single product across time will become a time series. Okay, so how many people do we have now? Participants are 8. Okay. All right, so you know what a time series is. Therefore, I typically will have a time series, say y, with respect to time. So its values are with respect to time. So we will say time 1, I have value y1, time 2, I have value y2, till some time capital T, wherein I have a value time t. So this is typically a time series, wherein we have only one variable, but its value measured across time. So as I don't remember who said, y could be price, y could be sorry. Y could be many other variables. Typically, I personally work in the finance area. So yes, Y could be price of any stock, the returns from the stock, and all that. Okay. Now, what we want to do is we want to predict. All right. Based on this known data, we want to predict tomorrow what will be the value of this Y. So we have data up till today from the past, and from there we want to know in typically a time series is to be able to predict tomorrow or any one period later. Maybe this is a monthly data, then next month, or if this is a weekly data, then next week, what will be the value of this series, the price or the returns. Okay, that is why we will typically do a time series analysis. Just let me see if there is anybody else. Okay, so this is the reason we will be doing a time series analysis, basically to predict what will be the value of Y tomorrow. Now, in order to do any prediction, I have to know how this person, how this guy behaves. So, you know, if I wanted to say how tomorrow what will be Smita's behavior, I need to know how does Smita behave, how does she behave in general over the past few days. So if unless and until I can understand, I can set a model as to how Smita behaves in the past, I cannot really predict how Smita will behave tomorrow. However, remember that this prediction is not etched in gold, because Smita might have behaved in some manner over the past 1 year, but tomorrow there could be a new situation and Smita can behave very, very differently. So probably over the last few couple of years, she has been studying hard and she was very serious. And tomorrow some result might be coming, which was not there in this data. That there was no. So she has been giving exams and all that. And we might have noticed that Smita is a very hardworking, serious bookworm, studies all the time, but tomorrow she has been studying and there was this exam, and then tomorrow the results might be out and suddenly we will see Smita is actually dancing, but we might not have seen Smita dancing in all these periods. So if we might be able to predict, we might not be able to predict in some cases if the underlying situation changes. All right. So one of the things that one of the drawbacks of any analysis is it is dependent on past data. And if that past data does not include the tomorrow's situation, then the prediction might fail. But if this past data situation continues, that is Smita's exams are still some time away and she's still slogging away, then this predicted behavior will be similar to what we have observed in the past. I hope that limitation of any time series analysis is clear. So that is one of the basic assumptions, that what has been going on in the past continues in the future. Okay, so any time series analysis or actually any analysis will completely fail during pandemic periods and all. So since many of you are PhD students that I can see, typically whenever we will do these time series analysis, we will try to take uniform times. I mean, we should not take in too much of volatile times. Let's say if we are talking about price and returns, we should not take pandemic like situation, or the 2008 there was a subprime crisis in the US which led to a lot of bad happenings throughout the world, etc, etc. So we should try to remove those data points when we are trying to model any series. Okay, basically when we are trying to model the series in order to predict tomorrow. That's why prediction of any so-called black swan event is very, very difficult, impossible actually. So prediction of any black swan event or prediction of any variable during a black swan event is almost impossible because you have so less data during such black swan events. All right. So now, so therefore, we come back that we have this y variable which we have recorded at different periods of time. So we have time here, that is t1, y1, t2, y2 till, let me write a few more, t3, y3, t4, y4 till t capital T, y capital. So the next concept that you need when you talk about time series is that of stationarity. To continue with my example, stationarity, okay, to give you a conceptual idea of stationarity, we want the series to be a stationary time series. What does that mean? That I can observe Smita only if she is there with me. If I see a girl who is always, I see going away from my home, going in from say riding a cycle in front of my window, but I just I have not been able to catch hold of her, then I cannot see what her behavior is, isn't it? So if I have to predict tomorrow what is the behavior of somebody, I need to be able to catch hold of that person. That person has to be stationary. I have to be able to observe and only then do the modeling. Okay, so that is stationarity. Stationarity means with respect to time, the properties of that person or the series remains the same. Now, what do we mean here? Strict stationarity is like this. So there are two types of stationarity. One is strict stationarity and the other is weak stationarity. The strict stationarity says, so what happens is when I see these behaviors, so if I say y1, y2, y3 are behaviors of a person, say Smita. So not every day she will be, studying. So some days we will see her studying very hard, very serious. Some days she might be studying a little, singing a little. Some days she might be studying a little, doing something else, etc., etc. So there will be some variation in her behavior, which means what I observe here actually comes from a distribution. So overall, this y1 has its own distribution. It can be sometimes a smiley person, a studious person, maybe a sad person, a happy person. So it has a distribution. So y1 comes from a distribution. The behavior I observe on day 2 also comes from another distribution. The behavior I observe on y3 on day t3 also comes from another distribution. So just let me know if you are following this, because distribution are values, possible values of y1 with some frequencies of this. So y1 probably comes from a distribution which is, it varies from this to this, and it is more possible that it lies in this region. So then we will say this is the distribution of y1. That is, y1 can come from anywhere from this value to this value, but more likely to be coming from this value. To continue with my example, Smita might be less of sad, little sad but more smiley, or sad, little less sad and more studious, and very, very studious most of the days, and a little less studious but happy on some other days. So these are possible situations that Smita's behavior on y1 can come from. Similarly, this is a distribution. Y1 values can come from this value to this value with most of the times lying in this region. So this is kind of a frequency distribution. This side is frequency. This side is possible values. Okay. Now Y2 also will come from another distribution. All right. Y2 will also come from these variety of emotions, sad, studious, happy. Now it may happen that Y2 comes from more of sad. So this is say sad, this is happy. And it comes from more of sad and less of happy. Okay, something like that, which means most of the time this person is sad. This then Y2 comes from another distribution. Stationarity says, the strict stationarity says, the distributions that Y1, Y2, Y3 come from are same. That is, Y1 cannot come from a different distribution from Y2. If it happens, then we cannot do any modeling. So basically what it says is, these are two different people. Somebody who stays happy most of the time and somebody who stays sad most of the time are two different people. We cannot model this Y at all. Okay. So the first requirement for a stationarity is that with time, the distributions from which Y1, Y2, Y3 comes, and Y1, Y2, Y3 are what you see on day T1, day T2, day T3. Okay, the requirement is that the distributions from which Y1, Y2, Y3 come are invariant with time. Okay, so what it says is, if I take, so the distributions are invariant with time. Does this make sense?
Yes. Can you give an example for this?
Yes. So to give an example here is, maybe say Y1 comes from a normal distribution with mean 3 and some variance. Y2 comes from another normal distribution but with mean 10. See, what happens is we will only see Y1, Y2, Y3. Okay, we will only see Y1, Y2, Y3 on each of these days. To take my example, we will only notice how the behavior of Smita on each of these days. But first we have to ascertain that these behaviors we are seeing all belong to Smita only. This behavior that we see should not belong to Smita, and this behavior that we see should not belong to Angela, right? Is that understood?
Yes.
So this distribution of Y1 and this distribution of Y2. So Y1 can take a, Smita can have large number of what should I say, emotions. There is a distribution of emotions in any person, but overall you can say, na, this person is very serious all the time. Another person is mostly laughing and happy-go-lucky. Do we say all this?
Yes.
Does that mean that the serious person never smiles? Or the happy-go-lucky person is never serious? That does not mean. So most of the time, somebody can be like this, and most of the time somebody can be like this. That means this distribution is different from this distribution. If Y1 comes from this distribution and Y2 comes from this distribution, we cannot do any modeling. Which means we are saying, strict stationarity says, why the behavior that we are noticing, we will notice only one value on day T1. And we will notice one value on day T2. But the underlying assumption has to be, so we have to prove that this, what we observed, came from a possible, today, anything could have been the price, isn't it? Say we are taking price of gold. This price could have been anything from, say, 45,000 to 55,000. right?
Yeah.
This price also can be anything, but if it suddenly becomes 20,000 to 40,000, so this is say 45,000 to 55,000, but this suddenly becomes 20,000 to 40,000, this distribution and this distribution, then we cannot do any modeling. So stationarity says that if you want to do any modeling of time series, they should both come from the same distribution. That is, they should belong to the same entity, same person, same series. Is that understood?
Yes.
Anybody has a doubt? Stationarity is a very important concept in financial time series or any time series. Anybody has any doubt?
Yes, ma'am. So this
Yes.
stationary concept, this is like important only from the perspective of modeling, or is there any real life significance, or
Yes, there is a lot of real life significance, and as we go along, maybe one, because I don't want to do a, see, time series can be a subject. In fact, here we teach time series as a semester wise subject. I'm going to do it in 3 hours, so I will not do a lot, but a little bit of mathematical modeling I will do, wherein I will show that this assumption is necessary. But it's not good to just make this assumption. We have to also prove it. Okay, so this assumption is important, otherwise we cannot do any modeling. Does that answer your question?
yes, ma'am. Okay.
All right, so first, this stationarity concept is important, otherwise we cannot do any modeling. Now it is very difficult to see whether from which distribution y1 is coming, from which distribution y2 is coming, from which distribution y3 is coming, and all that. So what is done is, there is something called a weak stationarity. Weak stationarity says, forget the distributions, but at least mean and covariance should be time invariant. What does that mean? It means that if I take this much of data, I can find the mean and, forget covariance, but as of now, variance, mean and variance of this much of data. And I can take somewhere here another set of data and again find the mean and variance. I can find the mean and variance here and the mean and variance here. Weak stationarity requires that the mean of this and the mean of this should be the same. The variance of this and the variance of this should be the same. Unless and until I can prove this, that the mean of this and the mean of this are same, and the variances are same, and also the covariance, I'll come to the covariance a little later, are same, we cannot go ahead with any modeling. So stationarity is a very important requirement. Strict stationarity says the distributions are invariant. Weak stationarity says, okay, distribution, we will typically, the parameters of any distribution is mean and standard deviation, or mean variance, or mean and covariance, mean variance and covariance. So if the mean and variance and covariance remain same across time, then we will assume that the distributions are also same, and so it is a stationary time series. Okay, so stationarity is very important. We have to prove stationarity. Now, so this is,
question.
Yes, please go ahead.
So, so say for example, here you have taken 2 samples where you have checked mean and variance, right? So, is it for a time series data? Say for example, there are 12 months. If I prove it for 4 and 4 months from wherever I choose, does it hold or for the entire?
Yes. Yes, no, it holds like that only. So when I calculate mean, so I will say mean. So if I'm doing mean, then I will say mean of, say, RT plus 1 to RK. Any set of data, T to, okay, T plus K. Let me take this as T plus K. So it could be 1, 2, 3, 1, 2, 3, or it could be anything. It could be 1, 2, 3, 4, 5, 6 to 10, whatever. Okay, anything should be equal to mean with RT plus L. I can go ahead by any number of values and then say RT plus L plus 1 to RT plus L plus 1 plus K. So what am I saying? Okay, let me just download some data and then maybe it will be easier.
But in that case, can we not sort of design a way to skip the seasonality part? See, for example, gold is sold during the Dhanteras time, right? So festival time. But if somebody asks me to check the seasonality, I check it for say January, February, March, and I do it for sometime other than November, December period. So three
Yes.
months I take, but I selectively take this thing out
Oh,
of the.
very good question. Very good question. So here you see, we are not putting any so you will not do this manually. You will do it. I mean, we'll come to the method, but right now I'm still going over the concept. Okay. So this L, you will not see. This L can be anything. I can take a lag of 1, which means I can take y1, y2, y3, and then y2, y3, y4. Okay. Again, I can take lag of say 10. So y1, y2, y3, and y11, y12, y13. So this L should not be selective. It can be any L. So to make this for all L greater than 0. This is more important, for all L greater than 0. So that removes the possibility that you select L such that you can get over this period of seasonal spikes.
Okay, so
Does
you
this
have to
answer your
do it.
question?
So we have to do it for the entire time
Yes,
series
yes.
that you are
So
taking.
yes, L can be 1, then L we will take 2. So R1, R2, R3, R3, R4, R5. Again, R1, R2, R3, R4, R5, R6. R1, R2, R3, R7, R8, R9. Something like that. So for all lags.
Okay, so you have to do for the entire.
Yes, but not manually. You don't have to do this manually, but that is the concept. So
To
if
check
I
the stationarity.
yeah, for stationarity concept. So if I have to, let me take some data. This is the Bombay Stock Exchange. This is the Bombay Stock Exchange website, as you can see, and I'll go down. There is this historical data. So I don't want any equity as of now. Let me go to indices. I don't know whether you are very familiar with financial things, but many of you, I think, probably will be. So I'll download historical prices. I'll take say Sensex, that is Sensex 50 only. But let me just select Sensex. Or else take Sensex. And this I'm taking daily data from let's say 2018 1st May till today. Today Saturday exchanges are closed, so till 27. Okay, I am taking on this data. So this is the data that has come, as you can see, from 2nd May 2018. 1st May is a holiday, May day, and then all the data is there. So I will download this data. This is my data file. Okay, so let me just see what we have. Okay, so you can see that. I hope you can see.
Yes.
All right. So on different days, these are the Sensex values. Fine. These are the Sensex values, and so if we had to plot it, then we would typically say insert chart. Maybe So forget the open high. You can see that during 2018, this was the kind of average. But after that, it's gone. It's increasing all the time. Only in this last in 2022 towards the end, again it is kind of constant. So you can see if I take a mean here and if I take a mean here, they won't be same, right?
Yes.
So if I take a mean here and I take a mean here, then also they won't be same. So then that means visually, but we cannot make any such comment actually. Visually, this seems as if this is a non-stationary series. If it kind of goes down, goes up, comes down, and we take different averages at different points of time, then we will see the values are different. So if I take an average here, 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 all for say 50 days or maybe 90 days, 3-month average. The 3-month averages will be different at different points of time. Then it is not a stationary series. The stationary series should be such that wherever I take an average, the average, say a 3-month average, daily data over 3 months, wherever I take it, the average should be the same. Okay, so that is necessary for a time series. I cannot do any modeling on prices the way it has come out. Okay, so this is how the price this looks. Sensex looks. All right, just let me go. So this is the Sensex value. All right.
So,
Yeah.
excuse me, ma'am. So I have a question. So this kind of series is not stationary, we say, or I mean, it's a weak stationary.
No, it is not even weekly stationary. See, what is weak stationary? Weak stationary is that the average, the strict stationary was they should come from the same distribution. The weak stationary says, okay, distribution we don't know, but every distribution has a mean and standard deviation. So if the means are same, then also we will say they are stationary. Here we saw that the means are not same. Right? If I take a 30-day average at one point of time and after taking some lag, I take another 30-day average, they may not be the same, right?
Okay, so this series is not at all stationary, you're saying?
Yes.
And if the mean are comparable or same, then we can say that, okay, it's a
weakly stationary. In common parlance, we will say, yes, it is a stationary series. Fine. That is the concept of stationary, that the average mean should be same wherever you take the data. So I will take a 30-day 3-month period, sorry, 90-day returns. Anywhere I take a 90-day returns with any value of lag, 1 day, 2 days, 2 years lag, whatever lag I take, but 90-day returns, the averages should be same. Okay, 90-day values, whatever, it should be the same. That is a stationary series. If it is not, we can see visually it is not, so then it is not a stationary series. The other thing is that it should also be, the variances should be the same. So whether I take a variance here, I think that went off. Okay, whether I take a variance here, or I take a variance here, or I take a variance here, or I take a variance here, they also should be the same. Now, variance is not very easy to see visually, so let us not even try to do that. But the variances have to be same. We also have to check not only whether the means are the same, but the variances also should be same for different lags. All right, which means what I'm saying is whether I take this set of data or this set of data and I calculate the variances should also be the same. Does that make sense?
Yes.
All right. The third is covariance. Covariance has a little bit more problem. So again, try to understand this. So let us not get into this anymore. All right. So covariance is like this. So This is close. Huh? So we will get out of this. I'm just taking this data and I am opening another. See, this is my P. T. So these are my prices on any day. So this is T1, T2, T3, T4, T3. All right, let me try to do one thing is that. So this is day 1, day 2, day 3, day 4, and so on and so on. Right? And I probably have 1000 days of data. Then is it visible or not?
Visible.
Visible? So we
Yes.
have this is my day. And this is PT. So day T. Let me call this day T. All right. Now, if you sorry. So this is day T and pre-T. So day 1, this is P1, this is day 2, this is price 2, this is by price P3, P4, P5. Now, what is covariance? Anybody remembers what is covariance?
It's the measure of direction of relationship between two variables.
Two variables. Very good. So covariance X and Y kind of tells me Xi minus X bar into Yi minus Y bar summation I is equal to 1 to number of data points, right? Covariance tells me how does X, the deviations of X from mean and Y from mean vary with each other. Whether Xi goes high when Yi goes high or Xi goes down when Yi goes high. Okay, so that is covariance. But covariance, remember, requires definitely two variables. In time series, we do not have two variables. So what do we do? What we will now do is say we will take this to be Pt minus 1. All right, that is, this is P1, or let me call it P plus. So if this is T equal to 1, then here I will say P plus 1, that is I will take P2. Is this clear? Here T is equal to 1. So this is P1. But here I am asking for P2 because T is 1. But I am taking T plus 1. So or when T is equal to 1, this is P2. This is P1, but this is P2. Is this understood?
Yes.
So what I am doing is I will take this. And now I have two variables. Okay, I have the original variable and this variable with lag 1. So whenever I have Pt, t is equal to 1, this is P2. This is P2, but this is P3. See, this is same as P3. So this is P3, but this is P4. Okay. So now if I have two series and I can find the correlations between these two, covariances between these two, this is known as autocovariance. Auto means autobiography, means when I'm writing my own biography, that is autobiography. When what is an auto rickshaw? A normal rickshaw is pulled by someone else. An auto rickshaw is when it is run on its own, when it is running on its own. Obviously it is an engine, but it's running on its own. So autobiography, auto rickshaw. Now you have something called autocovariance. Autocovariance means covariance on itself. Is that understood? But you cannot have covariance on itself. What is covariance on itself? What is covariance in itself? What is covariance x comma x?
Should not be any.
Sorry, it is
It's 0.
0.
No. So
Here you will
square
put
of
x bar and y xi minus x bar.
Okay, standard deviation. Okay.
Variance. Isn't it? Covariance of two variables, when they are same, then they give rise to variance. Is that fine?
yes.
Yes.
Okay. So whenever we are doing time series, therefore, what we will do is covariance between yt and yt plus some lag. Okay. So covariance between yt and yt plus 1, that is written as gamma L. Okay. Which means gamma 0 is actually, this is 0. So gamma t, covariance between yt and yt. So gamma t is nothing but variance of the series itself. But gamma L becomes a auto covariance. Is this understood?
Okay, yeah. So L is the lag. So it can
L
be
is the
1 plus
lag.
paper.
Exactly. So L is the lag. What does this mean for us? It means that I can, so when I take just this and this, it's the variance only. Just this and this is the original variance. So this is not important. Let me remove this. So this is not, this part is not important, but let me delete this. So this, if I find a correlation between this and this, it will be called gamma 1, because this is the covariance between PT and PT plus 1. So that is gamma 1. But we can also take P plus 2, which means when P is equal to 1, this is P1, but this will be P3. That means all data. So if I want to find out gamma 2, then I will take the covariance between this series and this series. Okay, this series and this series, the covariance will give me gamma 2. Why gamma 2? Because this I have taken as, this series is made by taking the second lag. All right, is this understood?
Yes.
So I can take any lag, say P plus L 10, and so when I have P1, this should be P11. So I'll go to P11, take this data and put this at P11. Now, if I find the covariance between this and this will be gamma 10. Fine? This will be the covariance between yt and yt plus 10. Is that understood? Anybody
Yes.
has any doubt?
So one doubt I have is
Please.
for to calculate the gammas, I mean to have this gamma, the length of, so basically pt plus 1, pt plus 2, t plus n should be a subset of p. I mean it cannot be
PT.
greater.
It cannot. Of course. Here you see, when I took PT plus 1, I lost 1 data point. When I took PT plus 2, I lost 2 data points. When I took T plus 10, I lost 10 data points. So when I calculate covariance, I have to do from here till, from here and here.
Okay.
I cannot do from here. Then though I cannot calculate, no? Because the covariance formula requires the same number of data points for X and Y. Correct? Is this understood? Autocovariance of the order L. Understood?
Yes.
Great. So now stationarity says all these autocovariances, that is gamma 1, gamma 2, gamma 10, gamma L, any value, should also be invariant with time. That is, whether I take this set to calculate gamma 1 or I take this set to calculate gamma 1 should not matter. They should all be same. Nobody, remember, is saying that gamma 1 has to be same as gamma 2. That is, if I take this and this, that will give me gamma 2. And if I take this and this, that will give me gamma 10. Gamma 2 need not be same as gamma 10, or gamma 1 need not be same as gamma 2. They can be different. But gamma 2 calculation, when I do, whether I take this set of data or somewhere here this set of data, should be immaterial. Is this understood? What is time invariance of the autocovariances? Just like when we were calculating means, we said whether I take an average here or I take an average here, it does not matter. Similarly, autocovariance, whether I take this set of two data or I take this set of two data, it should be time invariant. Gamma 1 can be different from gamma 2 and it can be different from gamma 10. Actually, they will be. Stationarity requires that which time period you take in order to calculate these autocovariances should not matter. Is this understood or have I confused you?
So again, sorry, I have a similar doubt.
Please ask 20 questions, no problems.
Okay, so the example which we've seen, so the series, the other series is a series or subset of one series, but then in practicality, we have this continuous time series data. So that gap which we've seen at the end, so that gap keeps on filling. So it means that, so the gamma which we would be calculating, so there would be, if it's a fixed time, so the number of data points would be same. It's just that the other points will refill. So this concept of covariance stands same for those.
As time progresses, my covariance does not change.
Yes.
Autocovariances do not change, but autocovariance of lag order 1 will be different from autocovariance of lag order 2, will be different from autocovariance of lag order 10. But over which time period of data I take to calculate this autocovariance should not matter.
Sorry, can you please elaborate? When you say that the autocovariance could be different for what?
Yes. So let me just do some gamma 1 is equal to covariance. So you see, Excel is asking for array 1 and array 2. Correct?
Yeah.
So this is my array 1 and this is my array 2. Fine. This is my gamma 1. But you done from B2 to B13, second row to 13th row of data.
Okay.
Fine. My gamma 2 is also covariance, but this is auto covariance because the data are same. So it is B2 to B13 and D2 to D13 because
is it necessary to take like 1 to 13? Can we compare this B1 to B12 versus D13 to D24?
No, that's a good question. So if I say B2 to B13 and you said D, what?
D14 or D13 to, yeah.
Okay, to keep it simple, let us say D12 to D23. This is what you mean?
That be gamma 2 plus another 12, right? So it will
Yes,
be
yes.
Gamma
T
4,
plus 10. That would be gamma 10 probably, or 10 or 11. whatever.
12, something like
Because
that.
now you are taking, see D already I have taken the lag.
Okay. Okay.
Instead you could say B12 to B23 would be gamma 2. Not actually 2, but it would be gamma 10.
Gamma 10.
But since I have already taken the lag in D, so I have to take simultaneously like that. So this is equal to covariance between PT and PT plus 2. Okay. So this and this are same, are different. Then similarly, I can take gamma 10. So this is a lag of 10. That means this is equal to covariance between price T and T plus. Okay. So you see this is becoming negative. T and T plus 10 is becoming negative. Right? Which means T and T plus 10, after the 10th day, the prices kind of goes down. As initially, as the prices were going up, after the 10th day, as the prices of first day goes up, from the 10th day, the prices are going down. That is the meaning of negative covariance. Now, this I have done all with 2 to 13 rows. But I can also take, say, 14 to keep it simply, 12 to 23 rows. Or let me say 22 to 33 rows. All right. Again, I can find a gamma 1, which is covariance. Sorry. Covariance between 22 to 33. That is 22 to 33. Here also, this is gamma 1. So I will take 22 to 33 only. Okay. So this is the covariance, gamma 1 covariance, 1 lag covariance. How do I find this as the 1 lag covariance between gamma 2 and gamma 3? So this is equal to covariance between 22 to 33. This is PT, but this is PT plus 2. Okay. So you see, these are both measures of gamma 1. This is also B and C, and this is also B and C, but over different time periods. This is B and D, this is also B and D, but in different time periods. This also we can do. So this is equal to covariance. So 22 to 23, 33, right? 22 to 33. And this one will be this. So these are the different values of the covariances. Now, stationarity requires that this value and this value should be same. Whether you take from these rows or from these rows, it does not matter. This value and this value should be the same. But this value and this value can be different. Similarly, this value and this value should be same, because here you took them from some rows and here same B and D. See, B and D, initial rows, B and D, later rows. So as long as you take B and D, these two values should be the same if it's a stationary series. But if you take 1 lag, 2 lags, so this is B and C, B and D, B and E, they need not be the same. Is this fine or have I confused you a lot?
So this makes sense, but then from these values, can we guess if it's a weak stationary?
No, so this is
stationary or-
not a this
No
is not a stationary series at all. Anyway, you saw the means were different. The variances will also be different. The covariances are all, everything is different. As time progresses, everything changes. The variances will also be different. Where did that go?
So any example of stationary time series data?
Yes, we will do all that stationary time series, I hope. It's already 11. So is this understood, first of all, the stationarity concept?
Yep.
All right, now we'll go ahead. Now, if this is autocovariance, therefore autocorrelation, if you remember, what was autocorrelation? If this is covariance, what is correlation? Covariance of x comma y divided by sigma x sigma y, or else divided by variance of x variance of y, isn't it? Remember, that is correlation. Correlation is covariance divided by the standard deviations, individual standard deviations. Do you remember?
Yes.
So in this case, autocorrelation between yt and yt plus L should be equal to gamma L divided by root over sigma t square and sigma t plus L square. All right, the variances, individual variances, because this is covariant, autocovariance between yt and yt plus L. So this also should be sigma t and sigma t plus L. Only in the case of a stationary series, whether you take sigma t or sigma t plus L, the variances are supposed to remain constant, isn't it? Only in the case of a stationary series, this can be written as gamma L by gamma 0. Gamma 0 is just the sigma t square. So sigma t square into sigma t square root over is sigma t square, which is gamma 0. Gamma 0 is what? Autocovariance between yt and yt.
Okay.
Have I confused you? Nobody is saying anything.
Not confused, but then, I mean,
Too much of information?
time. Yes.
So what should we do? So only for stationary series, whether you take a lag or whatever lag you take, the sigma t should remain constant. So this becomes sigma t square into sigma t square, which is nothing but sigma t square, which is autocovariance of the lag 0. This will take some time to digest, but let us go ahead because otherwise I'm already very late. So these are some concepts. So this is simply written as rho L is the autocorrelation, and this is given as gamma L by gamma 0. But this is valid only for stationary series, because only for stationary series you can write sigma t is equal to sigma t plus L. So this is sigma t square, this is also sigma t square into sigma t square root over is sigma t to the power of 4 root over. So sigma t square comes out from here. Sigma t square is nothing but autocovariance with 0 lag. So this is gamma 0. So rho L autocorrelation of lag L is nothing but autocovariance over lag L divided by the variance only for stationary series. Alright, otherwise we cannot write this equal to. This equal to is only valid for stationary series. Okay, let's move ahead. We wrote rho L is equal to auto correlation function. So typically, as we said, this is equal to covariance between yt and yt plus L divided by root over variance of yt and variance of yt plus L. For stationary series, variance of yt and variance of yt plus L is same because whatever lag you take, the variance is supposed to be remaining the same. So this becomes for weekly stationary series, rho L is equal to covariance between yt and yt plus L. We will take L lags of data above, and that is how we will do the covariance, and divided by root over variance of yt into variance of yt. We can write this because wherever we take the variance, after with a lag L or without any lag, they should remain the same. So root over of this into this is nothing but covariance of yt comma yt plus L divided by variance of yt. Okay, so this is known as autocorrelation function or rho L. We will say a stationary, this we can write only for a stationary series, and a stationary series is not serially autocorrelated if we can write that rho L is equal to 0 for all L greater than 0. Whether you take rho 1, rho 2, rho 3, rho 4, if we can show that rho 1 is equal to 0, rho 2 is equal to 0, that is that with every lag, whatever lag you take, they are equal to 0, then we will say that they are not serially autocorrelated. Autocorrelation means I am correlated with my own past lag. Okay, that is I am dependent on whatever I was yesterday or day before yesterday or so on and so forth. That is, if today's share price or today's gold price is say 50,000 rupees, tomorrow it cannot be absolutely 20,000. It has to be correlated to today's prices. So today's price is auto-correlated. It's actually correlated with yesterday's price. Yesterday's price is also correlated with day before yesterday's price, and so on and so forth. So we can say it is not serially, or that is serial autocorrelation if this is not equal to 0. But if it is equal to 0, we will say that the stationary series is not serially autocorrelated. Okay, these are concepts we will require actually. That is why I am kind of talking about them. So test for this is known as the Lume box test. So test for stationarity is has typical tests. Tests are tests for stationarity are called there's this very famous Dickey-Fuller test or augmented Dickey-Fuller test. We'll come back to this. And whether there is autocorrelation or not is tested by test for autocorrelation, test for serial autocorrelation, is the Lume LJ, Lume box test. test. So with this test, what it does is the null hypothesis of this test is that rho 1 is equal to rho 2 is equal to rho m equal to 0. All the autocorrelations, whether I take with lag 1 or I calculate the autocorrelation with lag 2 or I calculate the autocorrelation with lag m, they are all equal to 0. And alternate hypothesis is at least one of them is non-zero. Okay, that is my Leung box test. So Leung box test has a statistic. Typically, the statistic is q square m. Up till m lags we are testing, and what we typically do is if I have t data points, I will calculate the row correlations, square of the correlations divided by t minus l, whatever lag I am taking. So this is not t, sorry, this is lag. I will take all the different lags. So lag will be from 1 to m lags. So I have to test whether each and every one of them are 0. So each and every one of them are 0 means q square m will come out to be 0. Or they can be very, very small. So when I square them, they can be even smaller. So this value will come out to be very small. So that is the statistic. So if this is supposed to follow chi-square with m degrees of freedom, I don't know whether you have done chi-square test, but if this value is greater than this tabulated value, chi-square value at m degrees of freedom with some level of significance, whatever level of significance, 5%, 10%, 1% you're choosing, then we will say that there is serial autocorrelation. But if it is less than that, then we will say that there is no serial autocorrelation. If all the autocorrelations are 0. Typically, we will, whenever we want to do any modeling, we will try to reach this state after the modeling, not before. But the residuals should be serial autocorrelated, serially not autocorrelated. I'll come back to what is residual. I'm just going to ahead. This is still at a concept level. So this is a test for serial autocorrelation. This is known as the Leung box test. Okay, so so once we have this, again I'm slightly rushing. Is this understood, the Leung box test? What we are testing here? Any doubt? Okay, so I'm assuming that you are understanding and going ahead. So once we have this, we will now see. So what we see is typically the various series. We always have a series. Now we want to do some modeling. So what we have as I said, date t and some series y. So 1, 2, 3 till capital T and y1, y2 till y2. So first we have to satisfy ourselves that they are all, y comes from a weakly stationary series. That is, their averages, the variances and covariances are same irrespective of the time span over which I take I calculate the data. Okay, if I have mean, the mean should be same whether I take values here or I take values here. So first I have to check for stationarity, and if only once it is stationary, then I have to go ahead. Remember what I said, I have to find out what is tomorrow's data. This I do not know what is tomorrow's, but for that I have to see how this is getting generated. What are the means to generate this? So if that is the case, then what we do is first we see what are the possible tools that we can fit this data to. Once the data has got fit into that tool, then we can do the prediction. Okay, so so let us first look at what are the various processes through which y can get formed. So time series processes. Okay, so the first process is a white noise process. The white noise process says that Y is a sequence of independent and identically distributed values, which means they are so y, which means y1, y2, y3 are independent of each other. There is no correlation between y1, y2 or y2, y3 or y3, y4. They are independent of each other and they are identically distributed. That means they all come from the same distribution. So white noise is a sequence of IID values with finite mean. So the difference, this distribution has with finite mean and finite variance. Okay. So this, if they are not related to each other, this is independent from each other and they are all distributed in the same manner, then we cannot do a much of prediction actually. Then we are saying that, okay, we know that the expected value of tomorrow's value will be the average of all these values. And this, anything can happen from here. This average is the expected value. If you remember, the average in statistics is also known as expected value. So expectation of Y is typically the average of Y. So if they are independent from each other and they are identically distributed, we will say that tomorrow's data will just be the expected value of the past data. The mean of this past data is tomorrow's data. So typically, many times we have done this, you know, if we say what will be tomorrow's value, you will typically say what has been the average value over the past 10, 15, 20 days and say, okay, tomorrow's value will also be the average. So if I ask you what will be tomorrow's potatoes price, you will normally you'll say, over the past few days, on an average it was this. So tomorrow also potato price will be that much. So whenever we are saying like that, the underlying thing we are saying is every day the potato price or whatever price are independent of each other and they were all identically distributed. So tomorrow's price can be simply said as to be the average of the past prices. Okay, so this is the white noise. If it in the white noise, obviously because they are all independent of each other, so all ACFs should be 0. So in order to identify whether a series is white noise or not, we will find their autocorrelations and see whether they are 0. Actually, we will do this Leung box test, what we did just before. If the Leung box test comes out to be such that all these things are 0, autocorrelations are 0, we will say this follows a white noise. And the expected tomorrow's data is nothing but the expected value of the past data, just the average of the past data. There is nothing more that can be done. That there is no modeling required. You can just say it follows this. Okay. Now, so one special is called the Gaussian white noise. If YT follows normal distribution with mean 0 and standard deviation, not 1, sorry, some standard deviation or some variance. Let me try to erase this and write this. This is important. Say sigma square. Then, so in a normal distribution, everything are independent. So they are all independent from each other. And they are all not just simply identically distributed, but they are all normally distributed with the same mean 0 and the same variance sigma square. Then we will say this is a Gaussian white noise. Otherwise, even if they are not normally distributed, but it follows some distribution, but the same distribution with the same parameters, then also we will say y is a white noise. So this is a special case that of Gaussian white noise. All right? Confusing?
Yes.
All right, I will go ahead and I will see whether I can get time to get back again. Yeah, these are difficult concepts, very difficult to, we would typically have come back, reached this after 3 or 4 classes in a time series, but I am doing after 1 hour of a time series lecture. So obviously, this will be confusing. All right, so that was a white noise. Now let us look at auto-regressive models. Typically called ARP model. So just like we have learned auto-covariance, auto-correlation, auto-regression is therefore regression on itself. You have done regression till now. Let's say, can you give an example of a regression that you have done?
Linear logistic.
Sorry?
Linear regression, logistic regression.
A little louder, I can't understand.
Okay, linear logistic.
No, not going to logistics, just simple regression. Haven't you done simple regression?
Yes, linear.
Can you give me an example?
Okay, so you have default rates and maybe the default rates is your dependent variable and you have a independent variable, say the customer's age.
Sorry?
The customer's age and the probability of
So
default.
let's keep it that much. Let's keep it that. Fine. Great. So you see, whenever we do a regression, it has 2 variables. Obviously, that means auto regression will not have 2 variables. It will have the same variable but with a lag. All right. So AR, first let us look at AR1 model, auto regressive of order 1. What is that? We will say that today's value is equal to phi0 plus phi1 yesterday's value plus some error. So today's value depends on yesterday's value. Okay, in this manner. Now it need not be just one AR1. It can be AR2 model also. So AR2 model we will write as YT is equal to phi0 plus phi1 YT minus 1 plus phi2 YT minus 2 plus error. All right. Always we will have an error. Even when you do this regression, if you have age here and if you have a default rate, you will have different values of age. Correspondingly, you will have different types of default rates, isn't it? And when you do the regression, you actually pass a straight line through this data. Correct?
Yes.
At every value of x, this age, you have an error. At every value, you have an error. At every value, you have an error. Isn't it? So here also, for every YT, there will be an error. This is the basic model. There will be an error, always. It will never be exact. But then, we will assume that these errors are white noise. That is, they are identically and independently distributed and actually Gaussian white noise. That is, they have a mean 0. They all follow normal distribution with mean 0. But we won't get into that mathematics so much. So this is a auto-regressive of order 2. That is, past 2 values of y impact today's price of y. How do these models help us? If you see, notice, I have data till today. That means I can actually, if I can find out these values of phi0, phi1, phi2. First of all, I have to find out which of these models my y variable depends on. So I have y1, y2 till y capital T. Which of these models? And once I have the models, if I get y, phi0, phi1, phi2 values, when you do a regression, what happens? You get this value and this value, isn't it? And then given any value of age, you can tell me what will be the default rate, correct? When you do a regression, the idea is that you find out what is alpha 0 and what is alpha 1, isn't it? From past data.
Yes.
And then when I give you any value of age, you will multiply age with that value of age with alpha 1, with estimated value of alpha 1, add the estimated value of alpha 0, and tell me what is the expected value of the default rate. Hana? So here also, if once I know that this is the model, it could be this AR1, AR2, AR3, whatever be the model, from past data, once I find out phi 0, phi 1, phi 2, and obviously I have the data, so I want to find out y capital T plus 1, I want to predict, then this will be equal to phi 0 plus phi 1. If this is T minus 1. If this is capital T plus 1, this will be y capital T. Then small t is equal to capital T plus 1. So capital T plus 1 minus 1, capital T plus phi 2 y capital T minus 1. Okay. Then there will be no error because I do not know what in reality y T plus 1 will be. Error is between actual values. This is the actual value and this is the fitted value. Isn't it? That is the error. Here, I do not know what will be tomorrow's y, but I can give a predicted value of y, provided and obviously I have yt minus 1 and all that data I have. So I can easily tell you what will be the tomorrow's value of y. But for that, I have to find out these values of phi 0, phi 1, phi 2. First of all, I have to decide whether this is the model by which yt gets created, or this is the model, or which model. We haven't yet come to that. But this is one possible model type, ARP model. It could be AR1, AR2, auto-regressive. This regresses over itself. This regresses over itself. So auto-regressive models of order P. So if I had ARP model, I would write that as yt is equal to phi 0 plus phi 1, yt minus 1 plus phi 2, yt minus 2 plus phi p by t minus p. And at the end, I will always put an error. Okay, so this is the model and this is the error. Is that understood? ARP model?
Yes.
Okay, so obviously this will be highly correlated. Let us look at only this first value. Don't worry about the others. Let us look at only AR1 model. The other mathematics are very much more difficult. This I will only do this. The rest I will not do because they are very, very complicated. But this is to show you why we need that stationarity proof, why we need that stationarity assumption, and why we need to first check whether our data is stationary, else we cannot do anything. So AR1 model, we wrote yt is equal to phi 0 plus phi 1 yt minus 1 plus error t. This error is expected to follow a white noise, so normal distribution with mean 0 and some errors, some variance. Okay, so this error is supposed to follow this distribution. Now, so mean is 0 and this is the variance. So if I had to take just the mean on both sides, okay, expected value, I do not know whether you are familiar with this. Expected value is the mean. Expected value of a constant is a constant. All right. Expected value of a constant and a variable is equal to phi 1 into expected value of yt minus 1 and expected value of error. Fine, this is understood? Any doubt? All right. Now this is a generic thing, but for a weekly stationary series, expected value of yt and expected value of yt minus 1 are supposed to be the same. Because whether we take from t or we take one lag and then take the average, whether we take the average of the t data, t values, or we take one lag and then take the averages should be the same. So we have the average should be equal to mu 0, phi 0 plus phi 1 into mu. These two should be the same for a weekly stationary series. Expected value of yt is equal to expected value of yt minus 1 should be equal to some constant. They should not vary, but just because I've taken one lag, they should not vary. So mu should be equal to this, and this expected value of error is 0 because it follows, they are all identically distributed and they follow a normal distribution with mean 0. So what do we get? We get 1 minus phi 1 into mu should be equal to phi 0, which means mu should be equal to phi 0 by 1 minus phi 1. So this simplification we can do only for a stationary series. Otherwise, this just goes out of control, and we will see the random walk model will go out of control. Now, so therefore, for a weekly stationary series, so if we find that phi 1 modulus of phi 1 is less than 1, so then this becomes sorry, not less than 1, if it is not equal to 1. Anyway, if this becomes equal to 1, then mu becomes infinite. Then it again becomes a out of control. Okay. If this is not equal to 1, then we have this model exists, and we will be able to say that this is a AR1 model. So if phi 1 becomes equal to 1, this becomes 1, then this mu becomes infinite. So for a mean to exist, mean of this series has to exist, then this phi 1 cannot be equal to 1. Okay, so that is the idea that we get from for a weekly stationary series. So conversely, if we find that the phi is not equal to 1, we can say this is equal to a weekly stationary series. But that is not the end. We need another thing, that the variances and the covariance. So we will next let us take the variance of this. So variance of, I don't know whether you know this, variance of x plus y is equal to variance of x plus variance of y plus covariance of, plus 2 times covariance of x comma y. Do you know this formula? I don't know. I mean, maybe I'm doing too much of mathematics. Okay, let me skip all this. So again, I'm skipping this. I'm not getting into it. But if you can show that this variance is also the variance of yt should be equal to the variance of yt minus 1 and all that, then you can show. So I'm not getting into the mathematics. I'll get out of the mathematics. We can show that this variance is also equal to phi 1 by 1 minus phi 1 square. Okay. Again, for the variance to exist, this cannot be equal to 1. So phi 1 square cannot be equal to 1. Which means, actually, for the variance to exist, the phi 1 square has to be less than 1. Okay? This has to be less than 1. And so this can be done only for a stationary series. If it is not a stationary series, we cannot do. So which means phi 1 should lie not equal to, sorry, not equal to. Phi 1 should, if phi 1 lies between -1 to +1, only then we will have a weakly stationary series. Only then this AR model can be modeled. Okay, so these are, I mean, because I wanted to show you why we need that stationarity concept. That's why I did all this. But I hope with at least from this calculation, you got an idea why we need these to be stationary. Unless and until yt is stationary, we cannot write it this manner and we cannot do any modeling. Okay, so we need that concept of weakly stationary series. So that was an AR model. Okay, let us see whether we understood this AR model. This is an AR model. Okay. Another thing that we need to understand, but I am not getting into the mathematics, is that the autocorrelation functions of an AR model, you know, so actually you can show that lag rho of autocorrelation of the order L is equal to phi 1 square into rho of 0. Okay, this you can show. I'm not getting into the maths. Now, we have shown already that phi 1 square has to lie between -1 to +1. Therefore, that is because if phi 1 square becomes greater than 1, this becomes negative. Now, variance cannot be negative. Then standard deviation will become imaginary. So, variance has to be positive. So, phi 1 square has to be less than 1. All right, so phi 1 square had to be less than 1. So phi 1 has to be between -1 to +1. Now, if that is the case, then, sorry, this is rho L minus 1. Making a mistake. This is rho L minus 1. So rho 1 is 1. And then rho 2 will be phi 1 square, rho 3 will be phi 1 to the power of 4, and so on and so forth. So because phi 1 is between -1 to +1, that is 0.3, -0.5, +0.7, anything. So the square and the higher order terms will become smaller and smaller. So the autocorrelations for a AR model, AR say P model, the rho L's actually decays exponentially. This will be important to identify a AR model. Decays exponentially. At the rate of phi 1 and starting from 1. So typically, as the lag increases, lag 1, lag 2, lag 3, the rho L's start from 1 and then they go down. This rate of fall depends on phi 1. If phi 1 is 0.9, it will fall slowly. If phi 1 is 0.1, it will fall very fast, but it kind of decays exponentially. So that is how the autocorrelation function of the AR model looks like. Okay. So it kind of decays exponentially. There is also something called the partial autocorrelation function in time series modeling. So there is, I think I'm confusing you more, but there is also something partial autocorrelation function. I will not give you the formula and all that, but partial for an ARP model, partial autocorrelation function typically, I mean, there the so this is autocorrelation of lag L, then partial autocorrelation of lag L is actually not equal to 0. But so not equal to 0 for all L less than P. But as is equal to 0 for all L greater than equal to P. So if I have a AR2 model, then we will see that partial autocorrelation function. So if I have a AR2 model, then partial autocorrelation function of order 1 will not be equal to 0. But PACF 2, PACF 3, all this will be equal to 0. So if we see the PACF partial autocorrelation function diagram, then initially they will not be equal to 0, but suddenly they will all become 0. That will be a AR model of order P. So to identify an AR model of order P, we will look at ACF and PACF. Actually, we should not look at ACF because ACF, we will not be able to find anything. Rho L, this will just, the first value at lag 1 will be 1. After that, they will fall some bits at, but the partial autocorrelation function, what will happen is, at somewhere we will have some PACFs, okay, anything, non-zero PACFs. Then at least at some L equal to P, suddenly they will become 0. The PACFs will become 0. So statistically, they will become very small. Okay, from here we will say, oh, the ACF is reducing, but PACF was not positive till this. Only from PACF, from lag equal to 2, it has become 0. That means that means we are looking at a AR2 model. Is the identification understood? Because later on when we take data, we have to identify these models. We will plot the ACF and the PACF, and from the looking at those two plots, we will have to identify whether this is the AR model and what is the lag order of that model. Is this
so just once if you could repeat.
Anybody has understood or nobody has understood? Anybody has understood? All right, never mind. So we will get data y1, y2, y3 till yt. Some data we will get. I have already downloaded that data. Based on that, we will calculate the autocorrelations of different lag orders. Lag order 1, lag 2, lag 3. We just saw how to calculate this lag 1 autocorrelation. This was lag 1 autocovariance. But lag 1 autocorrelation you can calculate, isn't it? Rho 1 will be equal to correlation between this and this. Okay, then rho 2, rho, huh? Here I'm, okay, let me write them as rho 1. This is autocorrelation of order 1. This is autocorrelation of order 2. This is equal to correlation between the original series and this. Either you can do it this way or you can select from here only. Fine, but you have to be careful. You have to select the same size. Fine, is this clear? Or am I confusing you more? So if I have 2 lags, then if I start with 2, then I will, the next part we will start from plus 2, 4. Okay. So I don't need these anymore. These things I don't need. From PT only we should be able to find out. From PT only we should be able to find out rho 10. So autocorrelation of lag 10, that is equal to correlation between say 1 to 16. Then I want lag 10. So I will go from 12 to 26. Is this understood?
Yes.
So this okay, so this is the autocorrelation of lag 10. I don't need any more various series. Now, if you have understood the meaning of autocorrelation, it is correlation with some itself, but with some lag. All right.
Yes.
Okay. So these correlations. So with lag 1, I can find out one autocorrelation. With lag 2, I can find out some autocorrelation. With lag 3, I can find out some autocorrelation. If this series follows a ARP model, because just looking at those numbers, see, I can see just these numbers. From here, I have to identify which series they belong to. Okay, just from these numbers, first of all, this is not stationary, so I will do something about it. Then from these numbers, I have to find out what series they belong to. Only then I will be able to forecast anything, isn't it? So I have to identify which series they belong to. Is that understood?
Yes.
So once I have these values, yes, please. Some
Can you
question.
repeat this last part once?
See, I have these values of nobody has told me what series they belong to. Whether they are white noise, that is, they are just identically distributed, or they have some character like this. Nobody has told me.
Yes,
So
ma'am.
I need to identify, does this belong to AR autoregressive model? If I can identify that, oh, this belongs to an autoregressive model, then what will I do? I will go to the last day's data and then just put, like I said, if I can identify this is an autoregressive model, say of order 3. Order 3 means I will require, then I can easily get tomorrow's value based on today's value, yesterday's value, and day before yesterday's value. But I have to identify now. First, I have to identify which AR model this belongs to. I mean, this data belongs to. So how do I identify that? I will first get the autocorrelations for different lags and the partial autocorrelations. I will not bother you with the maths, but any software will give you. But the partial autocorrelations. Now, when I see for a ARP model, any data, if they are following ARP, what you will see is the partial autocorrelations are non-zero. But after one point, they suddenly become zero. That means, and the autocorrelation functions are diminishing like this. That means they are a ARP model with P equal to this value, where they suddenly become zero. The lag for which they suddenly become zero. Is this understood?
Yes, ma'am.
So maybe this is lag equal to 1, this is lag equal to 2. Suddenly from lag equal to 3, they become 0. Then you will say, oh, this is a AR3 model. If these are all positive, then lag 7, suddenly this becomes 0. Then we will say, oh, this is a AR7 model. But remember, correspondingly, the ACFs have to constantly keep reducing like this. All right. If phi1 is negative, then they will reduce like this. Okay, then it's slightly difficult, but it will still be reducing. Only thing is you will see it like this, but it has to reduce. Okay, once this negative like this, they will reduce like this and like this. But as the lags increase, autocorrelation function, lag 1, autocorrelation lag 2, autocorrelation lag 3, autocorrelation lag 4, 5, 6, 7, 8, as the lags increase, the ACF should look like this, the PACF will look like this. Wherever it becomes 0, then it is a AR model of order P. Fine?
We can only guess this through PACF, right, and not through ACF.
Correct. Absolutely right.
Okay.
Fine. Great. So this was an AR model. There can be another type of model called moving averages. MAQ models. Okay. Now, how does the MAQ model look like? So, MAQ model looks like YT will always have an error T. But if I have it like this, then YT minus 1 will also have an error T minus 1. YT minus 2 will also have an error T minus 2. Something like that. Fine?
Yes.
Okay. The moving average model says YT is equal to phi 0 plus, say, xi 1 error T minus 1 plus xi 2 error T minus 2 plus xi q error T minus q plus error T. Okay, so y's are dependent on the past errors and not on its past values. AR model was y depends on its past values. See, YT depends on its past. If AR1 value, it depends on the past 1 value. AR2, it depends on the past 2 values. ARP, it depends on the past P values. Okay. MA model does not depend on its past values, but it depends on its past errors. Fine. This is called a moving average model. How do you know that your data belongs to a moving average value? Here, ACFs and PACFs are just the opposite. So if my ACFs will be positive and suddenly from some lag, with some lag, and these are my autocorrelations, at some lag suddenly they will become 0. But the PACFs will always PACFs will keep coming. Okay? And depending on if psi1 is positive, it may be, you know, this side, that side, this side, that side, but value wise, they will keep coming down. So what did we see? If it is a ARP model, ACF will decay exponentially. PACF will be non-zero, but suddenly it will become 0. Then it is a ARP model. So we have to look at both ACF and PACF. But moving average, this will be non-zero, ACFs will be non-zero, and suddenly it will become 0 from some lag is equal to Q. From some lag is equal to Q, suddenly they will become 0. The PACFs but will keep reducing decay exponentially. Depending on what is your psi1, psi2, psi-q values, whatever, they will, but they forget the mathematical forms, but they will keep decaying. So this is how we will identify whether our data, again, please remember, we will only have data like this. We have to identify whether this is coming from a ARP model or a MAQ model. If ARP, what is the value of P? If MAQ, then what is the value of Q? Fine? Is this fine?
Yes.
All right, very good. And finally, we have something called the ARMA PQ models. Which is auto-regressive of order P and moving average of order Q. Here we will write y2 is equal to phi 0 plus phi 1 yt minus 1 plus phi 2 yt minus 2 plus phi p yt minus p, the ARP model, plus xi1 error t minus 1 plus xi2 error t minus 2 plus xi-q error t minus q plus error t. Okay, this is my ARMA PQ model. It depends on its past values. Today is y. So if I have to write y capital T1 plus 1, then it will become yt minus 1. All data we know. Error t minus 1, error t minus q plus 1 and all. So we will know all that. Now how do we identify ARMA PQ models? ARMA PQ models will be the ACF's autocorrelation functions will be non-zero and then suddenly 0. The PACFs will also be non-zero and suddenly 0. Okay. Now suppose, so where should I write? This L will correspond to P or Q? I don't know if he is taking notes. This L will correspond to? Yes, louder, you're right.
0, ma'am.
No, no. This has become 0. The PACS will become 0 from some lag. What will this correspond to, P or Q?
Q, ma'am.
Q? Let's
Yes.
see, PSPFs.
Q.
So if this is moving average of order Q, the PSF is supposed to keep falling. Okay. Only for the ARP, the PSCF is supposed to suddenly become 0. Fine? So AR part, this P will be P. And here where this suddenly becomes 0, this L will be the Q. So once you look at ACF and PACFs, this is how you will identify whether it's a AR model, MA model, or an ARMA PQ model. Is this clear? If it's an ARP model, or a MAQ model, or a ARMA PQ model. Is this fine?
Yes. Yes, ma'am. So, like, it remains the same. Now it is combining both of
Yeah,
the.
correct.
Yes, ma'am.
It remains the same, just it's combining. But you must know that PACF will give you the P value and ACF will give you the Q value. All right?
Yes, ma'am.
All right, great. And finally, one last, and this is a slightly difficult, it's called auto-regressive integrated moving average. So PDQ models. So this is auto-regressive. Then this I is for integrated. And this part is moving average. I will not get into the details, but in this case, y is not taken. A difference in y is taken. Difference to the order t. Now, what is difference? If I have y1, y2, y3, y4, y5 till yt, sorry. Then delta y1 is y1 minus y2. Delta y2 is y2 minus y3. Delta y3 is, or let me write it differently. 1 minute. So if this is yt series, then delta yt series is y1 minus y2, y2 minus y3, y3 minus y4, y4 minus y5, and so on and so forth. What is delta square yt? Delta square yt is this minus this. So delta yt was this minus this, this minus this, this minus. Delta square yt is this minus this, this minus this, this minus this, and so on and so forth. So del by this minus this is y1 minus y2 minus y2 plus y3. So it keeps on getting more and more cumbersome, but delta to the power of dy t means you just keep on differentiating, taking the differences like this, and then the final series that come up. So y2 will be y1 minus y2 minus y2 plus y3, and so on and so forth. This will also be numbers, isn't it? If these were some numbers, this will also be a series. Correct? Not clear?
Yeah.
Okay. Yeah. So once we take such D differences, then we will, on that series, we will put a ARMA PQ model. Okay, on that series, we will put a ARMA PQ model. That is phi 0, sorry, plus phi 1 y t minus 1 plus phi 2 y t minus 2 till phi p t y minus p plus xi1 error t minus 1 plus xi2 error t minus 2 plus xiq error t minus q plus error. Okay, so this integrated, this is more complicated, but because we'll look at softwares, they will give us the final version, not just AR, just as MA, but ARIMA. So this D, you need not worry a lot. Most of the time, D will be max to max equal to 1. Okay, so once we have that ARP model, MAQ model, ARMA PQ model, and ARIMA PDQ model, the last model that can be there and which is very common is a random walk model. Random walk model says that yt is equal to yt minus 1 plus error t. So this is nothing but the ARP model with phi 0 is equal to 0. So AR1 model, sorry, AR1 model, what did we write? Yt is equal to phi 0 plus phi 1 yt minus 1 plus error t. So random walk model says this phi 0 is equal to 0. This phi 1 is equal to 1. Okay, 1. Now, if you notice what happens when it is 1, so we can say y2 is equal to y1, let us leave the error. Y3 is equal to y2, but that is equal to y1. So, you know, it does not, it kind of keeps on, I mean, it does not go down and down. So this is it is a highly non-stationary kind of a model, and we have to remove this, remove the stationarity. And from here, actually, this concept of unit root, that is, this should not be 1. Earlier also, when we did AR model, we said that this phi 1 cannot be equal to 1. If it is 1, then it is a highly non-stationary. So from here, this random walk model, we have this test for stationarity. Which is the ideally Dickey-Fuller, but nowadays people use the augmented Dickey-Fuller test. So there is the Dickey-Fuller test, which basically what it does is it runs a regression between yt is equal to phi 0 plus phi 1 yt minus 1 plus summation of phi I delta of yt minus I. So forget all this. For I equal to 1 to p, some value, and then the Dickey-Fuller test checks whether this phi 1 is equal to 1 or not. If it is equal to 1, it becomes like this, and then it is not a stationary model. That is why it is called unit root test. Unit root test. The Dickey-Fuller test checks whether this is equal to 1 or not. And the augmented Dickey-Fuller test just takes a delta here, don't worry. So basically it tests whether this is equal to 1 or not. So the test for stationary Dickey-Fuller test, the Dickey-Fuller test or the augmented Dickey-Fuller test, the null hypothesis is that beta is equal to 1, which means series is not stationary. And alternate hypothesis is beta is less than 1, which means series is stationary. Okay, so whenever we will do the ADF test, remember we will have to reach here. So any software will give us the p value. If we get the p value, if we get p value greater than 0.05, what is our inference? Series is stationary or not?
Not stationary.
It is not stationary. And if it is less than 0.05, that means it is stationary. Fine. So we will do the augmented Dickey-Fuller test to see if it is stationary or not. And once we have seen that it is stationary, if it is not stationary, we will try to make it stationary. And typically we take differences. Most of the time, first difference makes the data stationary. You see, yt minus 1 is only equal to et. Then it becomes stationary. So errors are typically assumed to be white noise. So it becomes stationary once we take first differences. But sometimes we also may need to take second differences in order to make it stationary. So how many differences we need to make it stationary defines that D of ARIMA PTQ. So if we take one difference and the series becomes stationary, then this D is equal to 1. If we have to take two differences and then the series becomes stationary, then D becomes equal to 2, and so on and so forth. All right. So this is the augmented Dickey-Fuller test that we will do for stationary. Now let us quickly start the modeling part. I hope most of you are very familiar with Python. So everybody knows Python by now, right?
Yes.
Okay. So what we will do is then we will start a little bit of coding. So you do it through Google Colab or you have downloaded Python?
Downloaded Python.
All right. So anyway, either way you can do it. I largely do it in Colab so that I don't have to download it in each and every machine where I go to. So since you are doing it in your this thing, you can just start. So okay, first of all, you know that we will need some of the software, the packages. Just like in R, we have some packages. Even in Python, we will have these packages. Python is basically a software. So basic packages, import pandas as, so we will do import pandas as pd. Can you read? Can you see, or should I increase the view? It's visible. Visible now? Okay. Import pandas as pd and that numpy as np. Number by then as np. These are standards. Then we will also kind of, I don't know whether we can do a lot of plotting, but we will try to do matplot library. We will import the PLP. Okay. Then for that time being, let us keep it that much. Okay, we have to. We will keep on using data frame. So let me import data frame from pandas. Sorry. Actually, I don't need to do this. So I will need the data frame. Then what? I will need some time series data. So I will import time and something called KSON, and we will also import the date and time. There is this, it allows us to identify the dates from date time. So import date time from date time. I will import the date. This, and I will need import stats models. All my time series are there on. So once I have it, fine. But maybe I will directly call them, Just so from stats models, I will import the for that I will need the Dickey Fuller test now. So augmented Dickey Fuller is a software, is a package that is already there. I will also need the ACFs and the PSEF diagrams. So I will need these things from stats models. Okay, that is actually there in stat models, time series analysis dot stat tools. I think stat tools. Is from stat models. Within that time series analysis, then stat tools, we are importing Dickey Fuller test, ACF, PSEF. Then from again stats models, time series analysis is necessary. Then ARIMA model. So we will do ARIMA. Okay. And maybe we will also do from we would like to find out mean squared errors, so that is there in sklearn. Have you used sklearn for regression? So I think these are the ones that I will need. If I need more, I will come back. But as of now, these, let me see if everything runs fine. What happened? Should not take such a time. Okay, but in the meantime, you can get some data file for yourself. Like I went to Bombay Stock Exchange and I got okay. So I got this BSE Sensex values. Now you can also get some data. If you want, I can wait then for you to get the data. Or should I mail?
Yeah, I was requesting if it's possible for you to share the same file, so we'll be on the same page.
You can share in the chat, I think. You can find this.
Oh, I can share in the chat, is it?
On mail will suffice.
More comfortable with the mail. So let me. Don't want to trouble everyone. So I'm just putting 1%. Okay. All right. So I've sent it by mail. Maybe within 2 minutes you will receive this. So next I will, once my packages are all there. I will try to now get the data file. I typically like to, I do not know how you, but a collaboratory allows me to get import files. So I will get the collab files, but you need not Google .collab. I will import files and then this will help me to so I can data syntax. It's a big name. I don't want to be. Sensex is equal to b dot b underscore 6. Then this CSV get the date first. File name I can see here. Date. Okay. So now I should be able to read the file. It gives asks me to choose the files. I don't need to give any space, any path name and all. So this helps me do. So once I have this, so now I will convert this into a time series data. Okay. So as you could see, this has a lot of other values and all that. I think I hope it will take from this data only. Okay. So this is the CSV for date. I've got the CSV file, and now I will convert this into a time series with daily frequency. So I will convert data file into a time series format. Time series format, you can say. Actually, it will become from a list, it will become a time series. So import, I will need one package to do this, and I will say sensex date. This date will be equal to dd dot to, there is this so in 6 we have date this date. Actually, in the US, they use this may be a problem. Let me see. I may need to upload this one. So I will just change this to so we get day, month, year, But in the US, they recognize it as year, day, month, and day. Let me just see if it recognizes year itself. No, let me change this. So if I save this, it will automatically go. Let me read this once again. All right. So then we should have the date first. So what typically we will tell the software is that day first is true. Otherwise, it in the US they always take so the default is false, but we will make it true because otherwise it will not be able to recognize the date. Okay. So this will convert it into a time series kind of thing. So then we will say indexed and sets is equal to sets dot set index. I'm doing all this to convert into a time series. So then that date will become its index, not row 1, 2, 3, 4. The dates will become its index. So let me call price is equal to indexed SNX, but there I will only take the closing prices. Let me see whether this is coming correctly and whether the header is coming correctly. Something is wrong. This had made capital. Okay. Everything else is capital. All right. Oh no, it did not take it correctly. What happened? It's a data frame only. No? Let me give it a different name. SNX. This way. How do I convert it into a data frame? No, no, it's not coming to true. I imported data frame? I have imported data frame. So. Definitely make this. Okay. All right, let me not remove, let me try. I don't know what's going wrong, so I will remove this cell. And right now I'm not doing anything. I'm just taking SNX as closing price. I don't know what's going wrong. Without the date, I will have some problems later on, but let me see. Let this not. Why is it taking SNX closes? Should I come out? Can't get it read properly. This is bad. Let me see. It's taking this value is 35328. What to do? Any idea? Can you help me out? Can someone help me out here? Want to get that closed. So once I read this, it's reading this correctly. Then maybe I'll take just another. Okay. Where C is equal to SNX. PRC.head. I don't know what's going wrong. Such a close it is taken. Oh. Okay. Somehow it's not taking the close is going as a different thing. So it's taking the low. Okay. The date it's not taking correctly. So maybe I will say low. Okay. I will take the PRC only. Okay, this I don't know what's going wrong. I'll correct it. For the time being, I'll delete it. So I have taken only the low. Actually, I wanted to take the closing prices, but somehow it's the close prices are going to low and the date is getting mixed up. Something is going wrong. I don't know. I don't want to wait for waste time here. So we will go to the first thing. So first of all, let us just first we will have to check for stationarity. So we will check for stationarity. As we already know, we will not be able to get stationarity. So we can first just look at PLT plot. Here maybe we can see PLT plot. Here I needed the time actually. PRC dot values. Yeah, so this was the kind of plot we have seen earlier also. Now we will check for the stationarity of this data. So the code to check for stationarity is that the augmented Dickey-Fuller test. Okay, so one we will say that DF test is equal to, here it is augmented Dickey-Fuller. Sorry, this is the this is what we had imported also from stats model dot time series analysis dot stat tools. So AD Fuller we have taken. So it just gives asks for the file in the data, the lags till which you want to check, and then what you want to do. So we will just say augmented Dickey-Fuller test is with the time series. So what was the name of the thing that we gave? PRC, right? Maybe we will give PRC dot values. PRC dot values, and we will say find the whatever lag on its own from the AIC criteria. Okay. In time series there is a new what to say measure of error in when you did regression. I think you have done, if you have done OLS, you have done what is called the explain sum of squares and all that, error sum of squares. In time series we will do information criteria, say Akai ke information criteria or Bayes information criteria and all that. So once we have done this, let me just see whether it runs properly. Yeah. So this will give me the Dickey-Fuller test results. So then we can just get a printout of these results. So we will say Dickey-Fuller results is equal to ed dot series. Just this is just for printout so that you can so the test, the DF test, we will take the values, first 5 values in that. All those things will constitute of and this is why we will write this as this will be, we don't need the test statistic, but we can, if you need it, then we will need, it will give me the p-value, which is more important for me. What is the p-value corresponding to the t-test statistic? Then it will give me what is the number of lags it has checked for. No. What is the number of lags it has checked for? Then it will give, it can give me number of observations used. Number of observations, number of lags checked. So if you give it this way, then print DF results. Okay. Let me just see whether small, no, it's not capital, it is small. Okay. F does not match the length of it. Zero to 5 I have written, huh? 0 to 4. Okay, so this is the test statistic. This is the p-value. P-value is 0.81335. They have checked up till lag 7, and the number of observations, as we know, is 1001 data points that we have. So they have seen that there is stationarity. That is, what do we mean by number of lags checked? If you remember, we say in this we gave example of only 1 up till yt minus 1, but there can be yt minus 2, yt minus 3, yt minus 4 and all that. So it has checked up till 7th lag in this, and it finds p-value to be 0.83, 0.813. So what will be the what was the null hypothesis of my Dickey-Fuller test? The null hypothesis of my Dickey-Fuller test is that series is not stationary. And we said if p-value is greater than 5%, then our inference will be not stationary. So as we already knew, this price data is not stationary. So we will say if p-value, since p-value is greater than 0.05, so we go for null hypothesis, and implying series is that price is not stationary. So we cannot do anything with that price. Okay, so it is not stationary. Now, okay, so we have got this. Now, so our next point, next will be attempt will be to make the series stationary. Otherwise, we cannot do any modeling, right? So if I have to make the series stationary, what we can do is price. Actually, we typically we will take the returns. Now, we will say that price, or maybe we will say returns is equal to. So we will say is equal to NP dot log of price will give me just the logarithm of the prices, but then we will also take differences. Huh? So we will say NP log minus. So we are taking the okay, just one quick point that what I'm trying to do is get the returns. So returns is in finance. I don't know how many of you remember in finance. If I have P1, P2, P3 till Pt, then returns have two way. One way is to say P2 minus P1 by P1, or else we can say, so doing this in Python will be a little difficult if you are a beginner. So instead what you can also do return is ln of P2 by P1. And this is what I will do. So ln of P2 by P1 can also be written as ln of P2 minus ln of P1. Right? You know this? So what I'm doing is taking the logarithm of the prices minus logarithm of the shifted prices by 1. Okay, so this is what I am doing because this is easier to do. Here now the number of data points will change and we will face length issues. So I don't want to get into so much of detailed coding right now. I'm just taking this as np.log will give me the logarithm, and then I will do np.log of PRC. But then I will take this as one shift. Hope this works. All right. So once I know that this return works, maybe we can look at return.head. So next. So from the, see, first value has become NaN. So we have to be very careful about this. So the top ones. All right. So then, fine. We don't want this here. So we'll remove it, or we'll keep it with the hashtag. And so we have calculated the returns. And so we can actually now do the same Dickey Fuller test. I will just take this data to do the Dickey Fuller test once again and says check for stationary of returns. So we will again do the Dickey Fuller test, but now we will do it on the returns. Then let's see what we get. Okay, first value it will give me a problem. This NaN is there now, so it will give me a problem. So return values. Shall I do one shift again?
Can we not delete the first row?
How do you plan to delete the first row? Yeah, so how do I delete the first row? From 1 through length of, or maybe I can just do it here only, na? Return, sorry, return is equal to return 0 through, sorry, 1 length of return. This is necessary. see if this works. Yeah. Okay. So here that was a good suggestion. I removed the first row. The first row is return 0. Anything. The first row will be return 0. So I said that take the values from the second row, which is 1, to the final length of return. Okay. So I have renamed return, and then I again applied the same Dickey Fuller test. So the AD Fuller and then the Dickey Fuller test, the results of the Dickey Fuller test. Now you see the p value is nearly 0. Okay. So this is what, so here because the p value is less than 0.05, so we go for H0, implying that return is stationary.
H1, H8.
H1, H alternate, H1, whatever you say. So return is stationary. Okay. Once we have this as stationary, then we can do any modeling. Okay. And what did we see? That just one difference made the data stationary. That means also that my D becomes equal to 1. Okay. So with this, then we can now do ARIMA. All right. I have almost finished my time. I wanted to do a lot more. I do not know. Okay. So now we can, first we will have to, we still do not know. We have found out D, but we still do not know whether this return series, PLT, sorry. Let us see quickly what is this return series, how this return series looks. Okay. What happened? Should not take so much of time. So here you see, whether I take a mean here, the mean will come nearly 0. Whether I take a mean here, whether I take a mean here, means are almost equal to 0. What seems like is that the volatility may not be very constant, but because we have got this value, p value is very, very small. So it typically once you take first difference, all series become stationary. Okay. So once we have this, now we have to identify what is the ACF and PACF. So we will now plot the ACF and PACF, because we have to now identify what is the, whether it is AR1 model, whether it is ARP model, whether it is MAQ model, or whether it is ARMA PQ model, and what are the values of P and Q. So let us then do lag. Let me call this here R ACF is equal to, ACF is a function which I had already downloaded as, is a package basically. Is a function within this package. So I have already downloaded. So for me, it's very easy. I just have to give it the series. So for series, so it tells me what all I have to give in ACF. I have given X. By default, it takes 40 lags to calculate the autocorrelations. There are many other things we don't need so much. So we will just say, give me the ACF of returns and let it take n lags. Okay. And again, we will take return underscore PACF, which will be equal to just the PACF of this, of returns. If you type PACF, it will tell you what all functions you should be giving. So one is X, The other is, so for us, we will give returns. The other is number of lakhs, it will go up till 40. The method we will specify as OLS. Okay. This is a very special method. I also don't know what this method is, but it gives some problems. So we will just identify that the method should be OLS. Otherwise, it's just same. So we will say this is our returns. And we will keep the n lakhs to 40, but we will give the method as OLS. Right. So once we have this returns as OLS, plot. We will plot now the ACF and the so we will plot the ACF and PACF. So we will say, actually we want them to be in two different plots. I'm not very good at this, but maybe if somebody knows, I think I can write a subplot, no? Yes, I can give a subplot. I don't know, I'll just say give some numbers. And then I will say PLT plot. Return that same whatever I have on return ACF underscore ACF, isn't it? Return ACF. This I have some line. I don't want to give anything. Then another I will say PLT subplot. Because I want two different plots. So let me give it some other name, and this I will plot the PS. Let me see with okay. All right, now okay, maybe I have to make this a bit bigger. How do I make it a bit bigger? I don't know how to make it bigger. Plot size. Stay with this, but here, okay, here you can see this is the ACF. Okay, the first we plotted the ACF. This started from 1, as we know, and then it became very quickly it became 0, and here also it became very quickly 0. So this will be a little bit between, but we will assume that this has become 0, this has become 0. So I cannot really see, but I will assume that this is nearly after lag 1 it has become 0, and this after lag 1 it has become 0. So from the from ACF and PACF, I identify return is seems like ARMA P equal to 1, Q equal to 1 series. It seems to me that they are very, very same. Okay, very, very close to 1 only. So if this much is 10, I think from 1 only they have become zeros. Okay, from 1 till nearly 0. So at PQs. So we will try to set up. We will set up then an ARIMA series with P equal to 1, Q equal to 1, and D equal to 1. Okay. Now there is this catch. If I use returns, then I will use D equal to 0, because D after return is a stationary series. So for me, D is equal to 0 for return. If I want to put it on PRC, the price original thing, then I will make D equal to 1. Okay. Right now with return, I will just run this fit ARIMA model. Because
so with return we can use a normal ARMA model.
ARMA. The problem is P equal to 0 and Q is equal to 1. The problem is the software requires, ARIMA requires you to give a D. So we will give a D, but we will give it equal to 0 only. So after that it is very easy.
I'm saying, so we have a ARMA model, right? So basically, instead of ARIMA, if we go with ARMA, which requires only a P and Q, so once we have already done that 1 lakh.
But you know, sometimes, yeah, I understand. Sometimes you may have a D also. So it is better to use ARIMA. Don't get into ARMA. At least I personally always use ARIMA. So we will say return model. We will model it with ARIMA with returns, and order will be equal to 1, 0, 1. This will be my model. Up till now, is everyone with me? I do not know.
Yes.
Okay, I'm hoping you are with me. So then I will, I'm now, this will just give me this. I don't have to do anything. The software will give me all the values of of this. Okay, so what values I am looking at? So since I am saying that my model is a ARIMA 101 model, so what am I saying? I am saying return T is equal to 50 plus 51 YT minus 1 plus, sorry, not Y. I am saying this is equal to return T minus 1 plus Xi1 error T minus 1 plus error T. This is AR1, this is MA1, and I do not have any differentiation. So there is no delta here. So this is my model. And hence, what I will need is this 50, 51, and Xi1 from the past data. This the software will give me. Once I have this, I can easily predict tomorrow's return. Okay, so tomorrow's return will be 50 plus 51 return today, which I already have, plus Xi1 error today, which I already have. So this will be my prediction. All right. So first I have identified that this is a MA11 model. Once I have identified this is a MA11 model, I have to tell the software to give me values of 50, 51, and Xi1, because this is 1, 1. Is this part clear?
Yes.
Okay. Then, so this is what I'm telling. I'm telling the software, run this ARIMA. When it runs, the model will give me the values of so let's see, results is equal to we can just say summary, but maybe we will see is equal to model fit. Not model, return model. Before that, let us call for the summary of the results. Okay, so maybe we will say print let me say return summary. So we will do this fit. I think we will need to. Let's see. First, it will not give me the model. It will give me the fitted data. So I will fit the data to this, and then it will give me the results. Summary of the results. Let me see whether it runs or not. All right. So this is the result. What do we see? That we had run an ARMA 1-1 model because we said D is equal to 0. We have set D equal to 0. So it identifies that this is just a ARMA 1-1 model. And these are the errors. So lower the errors, better the model will be. So this is the error from Akaike information criteria. This is the error from Bayesian information criteria. This is the error from Hannan Quinn information criteria. Don't worry about this. These are done only if you want to. I mean, maybe you can run another model with 202. If you run this with 202, then check between 101 and 202, is the AIC improving? AIC improving means error should reduce. AIC should reduce. And log likelihood should increase. Okay, we maximize the log likelihood and minimize these errors. Okay, minimize AIC, BIC, HQIC and maximize the log likelihood. So if you run another model, check its output, these values. If the second model likelihood values are higher or the errors are lower, then you will say second model is better than this model. All right, that I'm just telling you, I'm not doing it and showing to you. So this is the so see, I needed this 50. This is the constant. This is the AR. So this is the coefficient minus 0.1642 and this is the MAQ, MA1 only. If we had given more than 1, then it would have given us data accordingly. So if you just quickly do this, I have already overshot my time. If you can give me 5 more minutes. So if you remember, this is 2931.3. You could have done it separately. 2931.3. So this likelihood is increasing, this AIC is reducing. So you can say 202 model is better than 101 model. So anyway, maybe whatever we have, let us keep it there. So this will be my fitted data. That means this is 0.0004 minus 0.1642 and all that. These are the values of 50, 51 and Xi1. I hope this is clear. Everybody understands that the software returns these 3 values to me. Okay. Oh, one thing I forgot to show you. If you give 202, ARMA 2,2, or maybe let's say 2,1. If I give 2,1, then my P. What is the meaning of 2,1? 201.
AR would be
AR is
2 and
2, MA will be 1.
Yeah.
So let us see. See, AR I have 2 values and MA is 1 value. Correct? But this is not a good model because I think the likelihood has fallen. So let us keep it at 202. If you do it, then you will get AR 2 values, MA 2 values and whatever. So this will be the AR 2 values and MA 2 values. This is the log likelihood. So you can just keep trying models. Whichever model gives you the highest likelihood and the lowest errors, all these errors, any one error if you follow good enough, because all errors may have different values, but they are monotonic. I mean, so once we have got this, so we have seen the results and all. Now we have to see whether the residue. So we have, this is something that the software has fit. I can take till 10 minutes, 13:10. I'll just quickly do what I was supposed to do. At least I wanted to do guards modeling also. Okay, so there are some model checking diagnostics. Just like in OLS, you had seen that you would check the adjusted R square. Remember? You would check adjusted R square. You would check the F value to say whether the model is good. Before you see any of these things, you have to first see whether the model is good. Once you see that the model is good, only then you will see the coefficients. And then once you have the coefficients, you will see whether those coefficients are significant or not. So here we have seen the coefficients are all significant. That is, the p-values are all 0. So coefficients are significant. That does not mean the model is good. So the test for model is that the errors should be all white noise. Okay, errors should follow white noise. What does that mean? Actually Gaussian. Okay, Gaussian white noise. That is ET should follow normal with 0 mean 0 and some sigma, some variance. Okay, so this is your model check diagnostics. Now to do this, errors should follow white noise and all this. If you remember, we said so for the above, conduct Leung box test on the residuals. Fine. We will conduct a Leung box test on the residuals. If you remember, the null hypothesis of the Leung box test was that, anybody remembers? That the thing is all 0. All the correlations are 0. If we can get null hypothesis, that means the error series is white noise. Okay. So here we will try to get H0. If it is not H0, then the model is not good fit. If the errors are correlated, then they are not good. Fine. Is this clear? So here we will write if H0, that is rho 1 is equal to rho 2 is equal to rho m is equal to 0, then residuals are white, not autocorrelated. That is, residuals follow white noise. That is, model is good. Model fit is good. Is that understood? If H0, rho 1, rho 2, rho m equal to 0, then residuals are not autocorrelated. That is, residuals follow, that is, model fit is good. Okay, so we should check if p value is greater than or less than. Greater than 0.05 to conclude that model fit is good. Okay, I am now hurrying. So we will now conduct the Leung box test on the residuals. So first we have to get the residuals. Let me return residuals is equal to, we will convert this to a data frame. Is the data frame not properly? So what did I give the name? Return results. This results, not resid. Okay, the results contain the resid. Okay, this residuals So we can print and all that, but we will not do all that. We will just quickly do the Leung box test. So we will quickly do the Leung box test. Just 1 minute. I just have to find out how to do the Leung box test. Forgetting how to do the Leung box test. Just 1 minute. So maybe we can plot the residuals. How to do the Leung box test? Did I download Leung box? No, I have not downloaded also. No, I can't remember how to do the Leung box test. So, Leung box test, how did I do the Leung box test? What did I do? I'm forgetting the Leung box test. No, I can't remember. Let me just check the Leung box test. So we need stats models. God. Downloaded stats models, right? Stats models. Okay. Receipt return. Receipt test equal to stats models. Sure, whether let's see whether this under PSA. It showed me, no? I've forgotten the Leung box test format, so maybe I will get back to you. I'll send you this code, okay? You just have to check the p values to see if the p value is, did they say stats dot not getting. No, it's not working. It's not able to find. So I can't remember the Leung box test where I had done it earlier once. Sorry.
Okay, ma'am. So can you share this Python
Yes, I will
code?
share the code. Yeah, I will share the code, but I'll fill this. I'll fill this Leung box test, how to do it, and then if it is good, then fine. If you get p-value greater than 0.05, then it's fine. If it is not, then that means this model that you have fitted is not good. So if the model is not good, then you need not even check these coefficients. They don't mean anything. So the model has to be good first. So you must do this diagnostic test whether the residuals are white noise or not. If the residuals are not white noise, then you have not done, the model is bad. So we will stop here. I'm sorry, I just forgot the Leung box test formula, the package. I'll finish this and send the code across to you. All right. If anybody has any question, I know this was a lot of thing in a very short time, but I hope you got a little bit of idea. If
Yes.
any question from anyone.
Ma'am, so is it audible, ma'am?
Yeah, you are very audible.
Okay, ma'am, for taking that lag, till how many lag can we test?
Test up till 20, 10, 20, doesn't matter.
Ma'am,
See,
ma'am, for that always it will be like increasing or decreasing trend of log likelihood value.
The likelihood, well, for a better and better model, if the model is improved, just assume likelihood as your R square.
Okay.
As R square increases, the model is better. As R square decreases, the model is worse. Isn't it?
Okay.
So take likelihood as similar to your concept of adjusted R square.
Okay.
Better you look at AIC. As AIC, any of this information criteria, this IC, if they reduce, that means your errors are reducing. Then a model is improving. But in any case, you have to see that the residuals are following white noise. That is important.
Then for each changing each lag, then we have to test for this white noise test.
White noise test. Okay. Unless and until you get a white noise test, it's actually in regression, you do that F test, na?
Yes, ma'am.
That is more important than the adjusted R square. Similarly, this white noise test, the Leung box test, is more important than just increasing the likelihood or reducing the errors.
Okay.
Okay?
Okay, ma'am.
All right. So these are the two model fit indices. One is this Leung box test and p-value, and the other is the likelihood value should increase and the errors ICs should reduce. After that, you see whether the coefficients are significant or not. So I will just do this and send it to you. I'm very sorry. Okay. So any other question? I've taken a long time extra. Okay. If nobody has any further questions, I will share the code and send it across to you all. All right. Thank you very much. And yeah, where am I? Yeah. So